Thank you, everybody, for joining us. I'm Mark Rotsart from Rotsart Dental Lab and Emerald Dental Works. Emerald Dental Works is the sidekick of Rotsart, and what Emerald is that's our area where we sell products. We sell the Medtech scanners, ExoCAD software, DG Shape, which is the Roland Mills, Austin Air Systems, and Zircon sintering furnaces. On one side here, we have in the webinar, Casper and Ralph will be talking about the pre-milled blanks. That is not yet Health Canada approved. And the other thing that we have up here is this is the new scan body. And the scan body that you see to the one beside it, the scan body is a full titanium scan body. So when you x-ray it, you see the full scan body, whereas the ones that they've had before is the peak scan bodies. So the top part is peak, and then there's a titanium interface with the implant. That titanium interface would be you'd be able to scan it and see it. But with the full scan body and the new peak and the new scan body 22s, they'll be easier to scan. It's a titanium, and they put a coat on it, almost like a Tynite coating on the whole titanium scan body. It's easier to scan intraorally, and it also, you can't really see in this picture, but it has a little hole in the middle of it. And what that hole is able to put a piece of floss through that. So if you're in the posterior using the scan body, you can have the floss just as an anchor point. When you screw that in, scan it, and then stick the floss out through it, unscrew it, and take it out. There's cleaning steps and procedures with this new scan body that we'll be going through. And in the new year, we're going to go through a whole new program with that. Let's get started with the presentation. This is the third of a series. Rolf and Casper have done 2 previous webinars for us throughout this year. And this is the third and final webinar. Quite interesting. It's very good. So let's start with the webinar.
Thank you, Mark, and thank you for the introduction. My name is Casper. I'm the Global Product Manager here at Elos, and I'm here with my good friend and colleague, Ralph.
Yeah, thank you, Casper. Thank you, Mark, again, to be part of this webinar. My name is Ralph Erhardt. I'm the Senior Manager of Sales and Technical Support in Germany. Okay, so let's start with the webinar.
Yeah, let's do it. Okay, so just a little bit about Elos. I know we mentioned this before in the previous webinars that we did, but Elos is part of the Elos Medtech group. We have 5 production facilities all over the world in 3 continents, and we serve 3 different market segments, orthopedic and life science, and then of course dental. And we are a little more above 600 employees worldwide. But Ralph, what are you going to talk about today?
Yeah, so let me introduce a little bit about the agenda. So we have 3 agenda points today. So the first one is the CAM software, the great unknown. Yeah, and as most of us are dental technicians or dentists, we already know that the education of a dental technician is much more about analog and manual processes, and not about using CNC programs or processes or CAM applications. That's why we want to dedicate a large section of our today's webinar to CAM software.
Correct. That's going to be very interesting. And as I mentioned many times, I'm not a dental technician. I don't have any dental background, but I'm actually a machinist. So this is actually something where I feel a little.
But you are feeling probably more comfortable with CAM software than me. Yeah.
But I for sure know all the hassles that also brings with this CAM programming. So it's interesting.
Okay. So the next point is the Elos Accurate Hybrid Base. So, but we want to go more deeply in how the library is created. What is the predefined fitting area, how works the CAD design, and how will it process in the CAM software? Yes. And the next one, or the last point on the agenda, is the Elos Accurate Primo Blank, which is a new development of Elos Medtech. Yeah. And here we also want to show how it works in the CAD software, but also how it interacts with the CAM software, because with CAM software, it's a much more complex topic using pre-milled applications, because you need always CAM integration. So the CAD output has to interact in some way with the CAM software.
Perfect. It's going to be great.
Okay. Okay, coming to the first point of the agenda. So I call it CAM software Gate Unknown. And as I already told you, digitization has been making its way into dental technology for many years now, but we are still more often familiar within analog processes. Yeah. And I think we have a long process chain of CAD/CAM, but we have CAD software, we have CAM software, we have machines, and I think with CAD software as a dental technician, you are much more familiar because you just exchange the instruments.
With a digital one.
Yeah, with the digital one. So you're using the mouse instead of the instrument.
Yeah.
But coming to the CAD/CAM workflow, it's much more associated to the job description of a CNC technician or mechanical engineer.
Yeah, exactly. And that's why we want to focus in this topic on the CAM application in today's webinar. And we have a guest today.
Yes.
We have Jago from Sim Systems on board, and he's going to provide us with some interesting insights into the Millbox CAM software. Jago will first discuss the more general functions of the CAM before we later talk about the application for milling hybrid abutments and pre-mill blanks. So please go ahead, Jago. It's your turn.
Thank you, Rolf and Casper. I'm very excited to be here and be part of this webinar together. So I will tell you a little bit about myself and the company as well. So my name is Jago Leal. I am one of the engineers at Sim System. And Sim System is the developer of Millbox CAM. That is the easiest and the better dental CAM software that we have on the market right now. Basically, in order to proceed with the Millbox workflow, we need to follow the steps that we have on our right side. So the first step will be clicking on New Job. The software will display to you if you want to change the project name. I will keep this one. Now we need to select our machine and as well our tools package, the tools that we are going to use at the machine side. This is very important for the software in order to avoid issues with the milling. Make sure that you have the proper tool set selected. Now we are going to select the material. For this case, I will select zirconium. And I will scroll down and select my fixtures. I have two in this case. I will select the first one. I will confirm and proceed with the next step. That is the import of the objects. This is one of the most crucial steps of the software. Here you need to import your STLs and select the proper restoration. This will dictate the strategy that is going to be applied for those restorations and also curves and surface that the software will try to create during the import. Here I have 4 cases, and in order to have a preview about the STL files, you can click on that. You have a static preview here, but if you click again on this image, a new window will open, and here you can rotate your file to have a better understanding about which is the type of restoration that you're trying to mill. All of these cases will be full contour hybrid, screw-retained crowns to be used with tie bases. And here I have 2 files from 3Shape, those 2, and 2 files from Exocad, those 2. The files from 3Shape I maintain the metadata, but the files from Exocad, I remove the metadata to show you that Millbox can handle files without metadata, and it will automatically create all the curves and surfaces necessary for the milling during the import. So after the selection of our files and the correct restoration type, we can confirm and proceed with the import. Here we can check that the software properly imported the files. So in this stage, we'll select our stock. By taking a look at the top, we can see the minimum thickness required for this case, which is 11.96. So we'll be using a 12mm disc. I have 5 on my stock. I can click here. And the software will suggest to me the disc with the highest percentage of use that will fit all the restorations that I have imported for this project. Here it selected the 37% of use disc. If I need, I can select a different disc as well. I will proceed with this one, so I will confirm. When I confirm, the software will nest my parts and will place the support pins. If I want to mill like this, I can proceed and save a toolpath, create my NC file, and start my milling. Otherwise, if you want to change something on the nesting, you can do it right now. So if you want to move your parts, you can simply drag and drop your STLs. If you want to rotate, you can use the yellow arrows to do so. And this is an easy step at the software. So for the support pins, it's the same thing. So if you want to move them, you can just drag and drop where you want the pins to be. We have 3 types and 3 shapes of support pin. And regarding the shapes of support pin, we have the round ones that you can see here. We also have the rectangular ones. And we have what we call smart pin, that is this one here. When you click here, as you can see, the pin will try to follow the equator line to avoid undercuts. In this case, I will use the round pin. For all of the pins, I can also determine if I want to cut them, do a semi-cut or not. So I will define 2 of them as entirely cuttable, the green ones, and the rest of them, instead of selecting not cuttable, I will use semi-cuttable. So at the end of the meeting, the software will do a pre-cut on those. After I finish with my nesting, then I can proceed with the meeting and click on Start Mill and Save Toolpath. The software will display to you some strategy options that you have available for these material restoration types and machine. If you want to have a better understanding about what that operation is going to do, you can click on the eye to see the toolpath that it's going to use. Like in this case, anatomic details. And in this case, I will select the undercuts to remove all the undercuts on my parts. And I will also use the 0.3 millimeter for anatomic details in this case. Once I confirm, the software will start the calculation of my strategy. And it will display to me the tools that is going to be used for this case. So make sure that you have all the tools available at the machine side in order to proceed with the milling properly. After the calculation is done, it will display a message to you informing the path where it's saving the file that you need to mill the machine. And after that, we'll have 2 types of simulation that will be available for us to use. In this case, we have kinematic simulation and residual. We're going to use residual for evaluate this case here. Once the simulation is done, we can take a look at the cavity area of our screw-tin crowns and see if, by the way, we can find any color different than gray that will correspond to a millimeter that we see here on this window. So by checking here, it seems that all we can see is gray inside of my cavity areas. So this means that we have no material left behind internally. And the toolpath that was created for those cases properly milled the internal cavity of these 2 STL files. And this say to us that we can expect from the milling of those cases to have a good fit regarding the shape of those hybrids. We can confirm, and then we can take that STL and start the mill. And now I'll return to you, Casper and Rolf, so we can discuss about the next subject.
Thank you, Iago, for the interesting insight in Millbox CAM software and its basic features. So let's look to the next point, to the Elos accurate hybrid base itself, and then talk about how the fit parameters are predefined in the CAD software and what you should pay attention within the CAM software.
Yeah, exactly. So a real quick glimpse at the hybrid bases. We have a few slides on that. So this is the hybrid base engaging from Elos. This one is the new H-line version. This is a taller chimney. You can see that it has a lot of features, and we're going to go through those. What's important to say here is that we have our locking mechanism, which is shown here with the blue highlighted areas, which is very important when it comes to the CAM software, because you want to make sure you mill locking area precisely and get the entire geometry with you, so you have that really nice fit of it. And of course we have our angulation, so we also need to talk about the angulated screw channel when it comes to the hybrid bases.
Right.
Well, if you look at the next slide, we just have an overview of the hybrid bases that we have. So here we see the engaging. You see the both version. We have generation 1 and generation 2, where we have the tall one and the shorter version. What's important to notice here is that we have our retention groups in the side. Which aids in the bonding process, where we gain a lot of retention surfaces, and the shape of it, which we're going to talk about in a bit, where we're going to look at the actual internal structure that we are milling. Again, both hybrid bases here have the angulation possibilities of the up to 28 degrees. If you have a quick glance at our abutment level. So here we have the non-engaging, meaning this is the abutment level hybrid bases. This one has a very nice feature where we have our guide grip that ensures that the hybrid base will actually stay inside the restoration, so you can actually just push it in, and you can use it for trying and handling. You can do your lab work without actually bonding it.
Yeah, that's a pretty nice feature, I think, especially for a dental technician, because usually you finalize your bridge or your crown and then glue it, and then you give it to your dentist, and then you put this in the patient's mouth and see probably there's something to change, but it's still glued on the titanium base. So this makes life much easier in the dentist office.
And again here, this small spring effect that we have here is also goes back to the CAM software, because again it needs to be exact.
Right, it has to be milled with the standard tools which are implemented in the software, right?
Exactly. And if you look at the last slide here, we just look at the features. Here we have the non-engaging. Again, we have the generation 1 and generation 2, and notice again the retention grooves on the side of it. This is a key feature when it comes to the retention, and we have our angulated screw channel. But let's look more into how the digital file actually works.
Yes, okay. So we talk a lot about the physical base now, or the hybrid base, but what's about the use in the CAD software? Yes, and we would like to dive much deeper in the associated hybrid base CAD library, and why the fitting parameters for hybrid base are predefined in it. Yeah, so there's still a cement gap predefined. So it's quite different to the cement gap you usually define with your crowns and bridges on dies, right?
Yes, exactly. So for us, it's very much important that we have our cement gap. The mating surface is predefined.
And if you have a look now, this is just showing how it is integrated in the library. So you see the red, the green color, the analog, and the hybrid base on top. But this is the crucial file.
Yes.
Even you are not really aware of it because it's not the physical part. We call it the base file, or the connection geometry in the library. And this is how the internal geometry of your cavity in your designed abutment works. Yeah, so you have already predefined the cement gap and everything.
Yeah, so this connection geometry file, it actually dictates the merge between the anatomical design that you're doing and the internal connection that will be inside the restoration. And this is governed by the library. And as you mentioned, like a normal crown where you can set the cement gap yourself, this is not possible here. Here it's governed by this file in the library, and we have preset a cement gap thickness on around 40 microns. And that we have of course, done a lot of studies to show what kind of cement gap is actually needed to have the optimal retention. And that's why we have this exact file to actually make sure that we end up in a situation where we have the cement gap needed. And what's also important here is to mention that it, of course, needs to be designed so it can be milled with your standard tools.
Right. Therefore, you need this tool radius compensation, right?
Yeah, so what you see in the gap above is that, of course, we need to mill the locking area, but we also need to make sure that the tool machines the entire connection geometry for the hybrid base. So that's why we have the gap above. This has been made so it can be milled with a 1 millimeter tool. So all radius here is 0.5. The design of this mating geometry, it looks quite straight when you look at it, but actually it has a 1 degree taper on each side.
Okay.
That also ensures that when you do your milling, you're always in the correct contact with the tool on the side of the restoration that you're milling. You don't have the tool dragging up against the chimney surface. So that will also ensure that you get a really nice milling each time, and it's optimized to actually fill, to feed into the milling machine and the strategies that it uses.
Okay. So the fitting area is already defined in the library. Yeah. So it's a bad idea to scan the hybrid base like a die, and then create your own cement gap. Yeah. Because then you have a very inconsistent and weird surface in your apartment, right?
Exactly, and unfortunately we still see that. And to some extent you can understand that if you don't do a tie base that often, purchasing the in-plan module and all that for the various softwares can be quite expensive. Yeah. But the idea of scanning a tie base and then design a crown on top of it, it doesn't give you what you actually need, and doesn't give you the value of the digital library. It doesn't give you all the information about the cement gap and the sizes, and get everything in the correct order.
Right, and you also get repeatable milling results using always the same file, which is imported or implemented in the CAD library.
Exactly. Yeah. I don't see how you can actually get the locking geometry to be correct if you were to scan.
Yeah, sure.
I don't think, but hopefully we don't see that much more of it in the future. But we have seen it. That's true.
Okay. So, but how does the predefined base file appear in the design process within the CAD software? So let's have a quick look into it and how the internal fit of the design abutment is created inside the CAD software. Yeah. So here you can see, I don't go over all the design process with matching a scan body. It's just to explain how this predefined base file is pictured in your later CAD output. Yeah. So, and if you see here, we have some angulated screw channels, we have some straight screw channels. Yeah. And if I fade in the let's say physical hybrid base into this software and make a small section view in it, you can see that this base file geometry is already pictured in the same way in your abutment. Yeah. So let's go to the section view and scroll a little bit, zoom in. Okay. Now you can see we already discussed it in the library, and that's what the library is creating in your final abutment.
Yeah, so here we're merging the anatomical design with the governance file from the library.
To make it a little bit clearer, I superimposed the final abutment with the CAD library.
Okay, so this is the library?
This is again the library, and you see this gap, and you see a section view through the hybrid base and its gap. And when you superimpose it with your final abutment, you see you already have the same gap now in your cavity of the created abutment, right? Yeah. So, you know, maybe also from the customer support that different technicians, different labs have different fittings. Yeah, so we have a lot of different zirconias in the market. We have a lot of different tools, a lot of different milling strategies, a lot of different sintering processes. And even we try to optimize this base file, the cement gap, also based on our cement study. Yeah, you can never balance it that everyone is happy with the same cement gap.
No.
Yeah.
Oh, and for sure, you can't change it in the library. That
Right.
is governed. And as I mentioned, we're aiming at a 40 micron cement gap.
Yes.
What we have done with the mating surface of the connection geometry surface is that we actually put it at 60 microns, because we want to ensure that we take into consideration the milling situation. It could be the accuracy of the burrs being used, the accuracy of the machine, the calibration, and all that.
Yes.
So we have some gap to play with.
Yeah, I think it's maybe comparable with the 3D printing process today.
Yeah.
When you have a model with dies in it, and you have different printers, different resines, different post-processing processes, and at the end, it hardly depends if you have a SLS or SLA or whatever printer, your result is always different. So you need to optimize the process or the settings to your individual process. Yeah. And therefore we would like to go back to Yago to show us how a user can optimally thread such hybrid abutments in the CAM software. So what features the CAM has for this purpose, and also how the fit of the abutment on the titanium basis can be optimized in the CAM software and adapted to your own individual manufacturing process.
Yes, for sure. Let me share my screen and we can discuss a little bit about the HBE, that is the hybrid base engaged files.
So same as before, we can click here a new job to start our case. I'll proceed with the name of this job like this. You can select your mini machine and make sure that the tool set that you have selected here is exactly the same one that you have at the machine side. Select your material and then scroll down and select the fixture that you want to proceed with this job. Here in this case, I will import two cases from Exocad, selecting the proper restoration type. This is very crucial. So here, instead of proceeding with the selection of the disk, I will cancel. And I would just make sure that all of my curves are properly identified here in this case. So for hybrids, there are three main curves. The prep line curve, that is the margin line, this pink curve here. Another important curve is the drilling axis, that is this green arrow on your screw channel. It needs to be exactly on the center of your screw channel. And also the red caps closing the screw channel. It needs to be like in the top and at the bottom part of the screw channel, like in those cases. We also have a non-mandatory curve here. This blue one is just to identify the emergency profile area, but this is not mandatory. So one important thing here is to check if you have the red caps properly assigned. It can't have any red cap inside the cavity. After that, we can proceed with the selection of the disk. In this case, it's a 1607. I will select an 18 height disk. I'll just confirm here. And then I will cancel. And then let's discuss about a few things that you should be checking here. So if, by the way, you are having chipping, of course, you need to check your machine and your tools. But it can be that the areas of your restorations are thin. So in order to check for the thickness, you can click on your part, click on the tools, and you see this option here to check the thickness of your STL file. By default, it will apply a color map regarding the thicknesses values that you have here. And then you can check for thin areas that you have by checking the color map here. Here, this part seems fine. You can also unclick this option to apply the color map on the external areas and see if, by the way, you have other thin areas. If you're having tight or loose fits with your tie bases, you can also apply a cavity fit to the software. You can click on your restoration, go on Tools, and then select this option to adjust the cavity fit. And here you have values to control the fitting of your cavity by applying plus or negative values. Negative values will make your part looser, like the arrows, and positive values will make it tighter. So you can select one of the options here and make your part like looser in this case. And as you can see, the software will display in a different color to show you that you have a cavity fit applied in that restoration. And of course, you can apply to the other restorations as well. This is very useful when you're meeting like hard materials, usually like PMA, for example, where the tool tends to deflect a little bit more and you have like tight fits. So this is a really good feature that we have in the software to control the cavity fit. If you need, you can increase that value as well. And you can also determine this value as default for the software. When you import those types of restoration, it will apply during the import and you don't need to apply manually after you import that part. In order to do that, we need to go on Tools and then Configuration. And then here we'll have an option for cavity fit. And you need to select the material that you want to apply that value as default, and as well your restoration type. So in this case, we'll be selecting full contour hybrid, and we're going to apply minus 0.025 millimeters as default. If you need like bigger values or different values, you can also click on these green buttons in order to change the values that you have here. So for example, here let's change to 0.07, 0.06, and then 0.05. And if you go back to the software, you see that you have those values now available for you to select.
Okay, thank you, Iago, again for this interesting insight into the CAM software. As we can see, the CAM software is not only an application to calculate the milling path, it's also a powerful tool to adapt the milling results to your individual needs, right? So, okay, but last but not least, we will come to our latest development, the Elos Accurate Primo Plank.
Yeah.
I think the main difference to other abutment applications is that you not only need the Primo plank as a consumable material, but also need a pre-milled holder to process it. Yeah. So the Primo planks allows you to design and manufacture one-piece titanium abutments in an easy in-house process.
Yeah.
So when we look at this animation, so you see that only the upper freeform portion needs to be milled out of the milling cylinder. So the implant interface is prefabricated.
Yeah.
Meaning its higher precision and fitting accuracy is to the implant is already defined and specified, right?
Yeah, exactly.
So that means you can, as an end user, you can easily focus on the individual abutment design of the upper part without having to take care of the fitting to the implant since it's already prefabricated.
Exactly. So why use a pre-milled blank?
Why is there need for a one-piece titanium abutment? Yeah, so what is the indication to use it? Yeah, so we all know today that ideally the abutment should follow the anatomical later prosthetics, right? So in the sense of a backward design, and therefore it has to take into account the individual anatomic conditions of the patient. So what are the today's alternatives? Yeah, so let's have a look into the stock abutment here. And we see with a stock abutment, you never follow the natural gum profile, right? So you have a lot of let's say, disadvantages in using stock in using stock abutments. So they are often under-contoured and so really poor support for the prosthetic crown.
Okay. But then we have our tie-based
Yes,
solutions.
we just talked about a hybrid base, and it creates you a lot of advantages doing very aesthetic and individual customized abutments. But
I guess
It's
it's
a-
not for everybody.
Yes, I think it covers a lot of indications at the end. But however, in some cases, this may not be the ideal solution, even if it allows you angled screw channel like Elos accurate hybrid base. Yeah. So, for example, you see it a little bit on this picture. Sometimes you have a very limited space. Yeah, and then you need, due to the minimum wall thickness of both the titanium base but also zirconium, there's no need to have wall thickness, and so the abutment will be thicker than you probably need it. Yeah. Also, you have less or small design freedom in case of very angulated frontal teeth.
Of course, yeah, yeah.
So especially in the frontal area, sometimes you have very narrow gaps. Yeah, and then if you put in a hybrid base and add on the minimum wall thickness of a zirconia abutment, it fills the gap completely without having the crown on it. Yeah. So when we look at a pre-milled abutment, it can offer you a very good alternative here, as it allows you to set the starting point for the angulation of the abutment almost closer to the implant shoulder.
Okay.
Yeah. So it also offers a very good stability when the space is limited, because there's no need to combine different materials.
Okay. So that's the whole philosophy about the pre-milled blank. A little more design freedom in these critical areas.
Yes, more angulation of the abutment itself, not just about the screw channel. Yeah, also more stability in cases you have limited space and so on.
Okay.
Yeah, you create, so to speak, your own gingiva height.
Yeah.
You can say that.
Yeah. So more freedom.
Yeah.
A little more freedom. That's good. Okay, so just a quick glance at the new Elos pre-mill blank. We have a lot of features here. We're not going to go in through in details, but we have our locking area, which is important because we need to know exactly where the pre-mill blank is in its holder. And here we see the holder. Here we have the holder with the pre-mill blank. And again, a lot of features. This is not what we're going to go through now, but here we see the modular system that we have. And what we're going to go into next is the importance of actually making sure that the machine knows exactly where the position of the pre-mill blank is and where the abutment that you design actually fits into that. And that's the whole integration part about this pre-milled solution that is crucial, and where the cam plays a very big role.
Right, right. So it's not just about the precision of the physical parts here.
No.
It's also about the precision, how it is implemented, how accurate it is implemented in the CAM software. Right.
Exactly.
Let's have a briefly look into the software and the CAD software, how to create this abutment. You
Yeah.
see, after you positioned your anatomical tooth, yeah, you are allowed to design exactly your abutment following the angulation of the crown axis and whatever. And you can see it in the section view that you can easily shorten it, angulate it, adapt it to your anatomical outer shape. Yeah, so the tooth is like a digital shell around, and you can adapt the abutment very easy to it. Yeah.
Okay, so this gives you a little more design freedom, and you can
Yeah.
do a little more customization.
Right.
But you also need to be able to actually machine what you design.
Yes, right. Yes. And you see here in this case, you can create your own gingiva height, as I told you.
Yeah.
So that makes it pretty nice to support the gum and to relocate the cement gap to the upper level of the gum.
Yeah.
Now you see the pre-mill blank and how it's finalized with the screw hole on it. Okay, as we already learned talking about the features of the pre-mill blank and the corresponding holder, the correct positioning during the milling process is one of the most important requirements here.
Yeah, absolutely.
So in order to prevent the blank from being positioned incorrectly in the XY plane, we have designed these green marked areas in the holder module and blanks, so that the blank is always fixed, stable, and clearly positioned in the holder.
Yeah, and this ensures us that we have the blank where it needs to be.
Yes, right.
So now we need to tell the machine where the blank is.
Yes, right. So the same we have for the height offset. Yeah. So an offset in the set plane would result in an abutment shift, meaning that the height of the abutment would be too high or too low,
Yeah.
and that it's maybe not in the right position relative to the prefabricated implant connection. So this small animation shows you how the blank is automatically pulled down to the
position, yeah.
module, into the position, which is not just important in regard to the physical position of the blank. It's also important that this position is also the same in the CAM software.
Exactly.
Yeah. And this easily bridges to the CAM software and the importance of the correct position of the Primo blank inside the CAM software, not just in the machine.
No, exactly. So let's have a look at that.
So from a mathematical perspective, whenever we talk about the position of any object, we are always talking about coordinates of an object, right?
Yeah.
So you may know this topic from your GPS tracker, or for example, a chessboard is also a coordinate system. It's a two-dimensional coordinate system where it precisely describes the position of your figure on the chessboard, right? So since each position of an object in a milling machine has a specific coordinate, a reference system such as a coordinate system is required as part of the kinematics of the machine.
Yeah. So how does this really look?
Yeah, and now you see it how it looks in the machine. Yeah, for sure the coordinate system is not visible like in this picture. Yeah, but since the milling paths for milling the pre-milled abutment are calculated in CAM software, each individual position of the milling tool in the milling path is a single coordinate. And if we superimpose it with the CAM software, you see you have the same coordinate system inside the CAM software. So it has to match to the machine.
Yeah.
Because otherwise the milling paths are calculated in a different position. Yeah. So the CAM software doesn't know what the CAM is calculating and what position the CAM is calculating. Yeah. So we have two coordinate systems.
Yeah.
One in the CAM software and the other one in the machine.
And it needs to align perfectly to have the desired
It has
result.
exactly to align and match. Otherwise you have deviations in your milling result.
Yeah. Okay, Ralph, so what happens if these things are not aligned? And I guess we will see something of what you display here.
Yeah, maybe it's not, it's a bit dramatic pictured here, yes, but at the end you will have maybe a poor surface of your milled abutment.
Yeah.
Yeah. Or in worst case, you probably have a tool break or a collision inside the machine. Yeah. So it's important to remember that a holder and a pre-milled blank must be manufactured both very precisely so that the blank is always positioned correctly in the holder and that the physical position of the blank corresponds to the already defined position in the CAM software.
Yeah. So that's the manual handling here. You need to make sure that the pre-milled blank is in the correct position.
Yeah.
We need to make sure that everything is clean.
Right.
So you actually have a good seating area and a precise seating area.
Right. So if you have grinding chips inside the slot of your holder or whatever, you have to clean it before.
Yeah.
Because otherwise the position in the machine is different to that position the CAM expects the blank.
And then you will not end up with what you actually expected from it.
So yeah. That's right.
So what are we seeing here?
Yeah, I think when you create your design in the CAD software, you're always really focused on the STL file.
Yeah.
So everybody knows when I create a file, when I create a crone or a bridge or an abutment, you get an STL file. And that might be the most important file for you because it shows you
the design.
The design, yeah. But on the other side, it transfers nothing of additional information.
It's not really a CAD file.
No,
it's a point cloud on a surface.
It's a triangulated point cloud,
Yeah.
not more. And it gives you no information about probably the implant system you have used, the orientation, what kind of blank, a Primo blank is matching to this abutment. So no additional information at all.
No. So we need more than this.
Yeah, there need to be more in the CAD output like this. Okay, so the STL file is some kind of stupid, so to speak.
Yeah, it doesn't contain any information,
Right.
basically.
So you need the metadata, and the metadata is also generated in CAD output. So it's not just the STL file. So if you look in it, for example, with Exocad, you have this construction info file with a lot of coordinates inside it, and nobody opens it and read it. Yeah. But for the CAM software, it's very, very important because there is all the information embedded in this file, which the CAM needs to detect the right blank, to detect the right positioning of the button in the blank later in the CAM software.
Okay, and I think we have an example of it here, right? So what are we looking at here?
Yeah, this is, for example, this is a very small section of the construction info. So if you look into it completely, then you scroll down maybe 10 minutes. Yeah. So, but if you look at it, you see, for example, you see this implant descriptor line, yeah, inside this construction info. This is, for example, the keyword the CAM needs. So when we talk about CAM implementation, this keyword has to be implemented in the CAM software. And then when you import later your CAD file with the construction info, the metadata, then the CAM read this XML files and try to find the right keyword. And if it finds the already known keyword of the CAM, then it matches. Then it easily knows, okay, I have to call from the database the right blank. So if it's a stroma and bone level, for example, it says in the keyword, this is a stroma and bone level. It's the Elos Accurate system. You have the system automatically calls up the right folder and so on.
Okay, so everything is automated.
Yeah,
And this
everything is
will also
automated.
place it in the right position.
Right. Everything is automatically nested. So we talk a lot of complexity here
Yeah.
of CAM integration, all this, but it's just to give you a small picture how it works. So, but in the daily work, it's much easier. So we just import it, and it's a fully, let's say, plug and play process using it.
Okay, but I guess Jago's gonna show us how it actually works.
Yes, right. So Iago will also show us in the CAM software how easy it works. Yeah. And so, Iago, let's go.
Yes, let's discuss a little bit about the preview blanks. The workflow is pretty simple, and it's very similar to the other workflows that we have at the software. As you know, first we need to click on New Job, select our job name. In this case, I will select the 350i Pro machine. For the premium blanks, I will select titanium material, and you should have the fixture, like this is the Elos fixture. It should be available for you if you have this on the software. After selecting the fixture, you can select the position, and for this fixture specifically, we have 6 positions. I will select number 1. And now we can import our file. So same as before, I have here 2 files from Exocad and 2 files from 3Shape. All of them has metadata. So when you have a metadata file like this one, when you click import, as you can see here, we are on the 3Shape folder. When you click on the import, the software will read the metadata and will automatically import the correct blank for you, because we know exactly the CAD library that was designed for this case. So here I'll just hide my red caps, and I will enable my fixture so we can see it. As we can see, our abutment was properly imported and it was nested on position number 1. So here there is nothing I need to do for the nesting. It's pretty straightforward. If I want, I can proceed with my calculation now, but I will import another abutment on position number 2. So now I will import an Exocad file here, and same as the 3Shape file, I have the metadata, so the software will find my block and it will import it automatically. I don't need to do anything here. Okay, so now let's take a closer look on our case here. As you could notice, the software did all the nesting automatically for me, so the position seems to be fine. It placed the support pins in both cases with the correct diameter. So it seems fine in this case. I will import the third case. But in this scenario, I don't have the metadata. Okay, so this means that the software doesn't know exactly which is the interface by checking the STL file. So what I will do here, I will basically import my file without metadata. And the only thing that I need to do different than the others is that I will manually have to select my premule blank. So in this case, this one. So I will just select my blank and I will confirm. After the confirmation, same as the other cases, the software will place my STL file on the blank with the support pin, and that's it. Now we can start our calculation. So when I click on Start Mule and Save to Path, the software will display to me some strategy options that I have for such cases. In this case here, I have 5 options. So let's discuss about the first 2 options. So this one, Finish Emergence Area. So this means if we click on this option, the software will apply another finishing on the emergence area. The retention option will mill some grooves at the top cap part of the insertion, so we have a better cement. So I will select the emergence finishing and also the retention with the 1 mm ball. I will confirm, and now we just need to wait the software to calculate. Same as before, the tool list will be displayed to you. Make sure that you have all those tools at the machine. Now with the calculation finished, let's check the kinematic simulation. In order to check for the kinematic simulation, you click on Simulation and then Kinematic Simulation. Once the simulation is open, we can maximize that. And I know it has a lot of options here. There is no need to be afraid of a simulation. Basically, all we have to do is to run the file. And if we need, we can hide a few options here. So I just hit the 2 path. Let's take a closer look. So here at the kinematic simulation, you can see the movements that the machine will be doing to mill your case. You can speed up this process if you want, or you can simply drag and drop the progress bar at the bottom for a fast end result. So we can just drag and drop this, and the software will calculate the left material. So now that it's finished, let's take a look at our result. So this is the result that you should be expecting that the machine will deliver to you. Let me hide my tool here. So these grooves that we see here, they are caused because of that option that we marked at the strategy option to mill the retention. So this will create like retention grooves in order to make the cement with the crown better. As we can see here, it will create those small grooves. This will create mechanical retention for the cement to be better. So when you will be cementing those abutments on the top crown, it has a better mechanical retention. So this is the result that we should be expecting to see at the machine. Of course, the machine needs to be calibrated with the correct tools in place and everything else. I would like to thank you for your time, and I hope you appreciate what we discussed here.
And if you need something from us, just reach out. Thank you.
Okay, thank you, Iago, again for this deep insight, and it was pretty easy to use.
It looked really
We
easy.
we talked a lot of coordinate systems, so we can't forget it again.
Yeah.
No, it's pretty easy. So everything is automatically nested here.
Yeah, but it was interesting to see actually what goes on behind the scenes, because it is really complicated and there's a lot of work into it.
Yes, and if it doesn't work,
Then you know it's
then it helps you to get a little bit more background, because there is a CAM implementation missing, or you have not the right version of the CAM, or you didn't update your database of the CAM. So it's good to know a little bit of the background to handle it if there is coming up any issue in this process.
great. Yeah, well, thank you to Iago, and thank you for watching this webinar. We hope it has been useful and interesting. So
I hope so.
yeah, until next time.
Okay, bye-bye.
all the Elos products. What we have is a scanner here. This is basically go to our store and order products that you would need. On the other side here is Derek Kent. We've asked Derek, he's our inside technical guy, to do a brief description on downloading library, installing libraries and updates in the library. This is a 7-minute video and it's a YouTube video. I'd like to thank you for joining us today for this webinar. And we have a few more webinars that we have in the process and planning in the new year. The first one will be on the brand new scan bodies, and that'll again be with Elos. And if there are any other topics or webinars that you guys would like us to do, please drop us a line and let us know. So I just want to say thank you for your time. Pleasure having everybody here, and take care. Goodbye.